Okay, let me describe how to set up this problem that we're going to use to do parameter estimation of a tracer that will be used to evaluate porosity and dispersivity. So the analysis will use a geometry that is shaped like this, a square domain that has a circle right here. It'll be 2/10 of a meter on a side, and the circle is 1 centimeter in radius, and it's located halfway up on the y-axis and at x equals 0.04. This will induce a flow from left to right, and this will be a zone, a little circular patch of concentration that we put in, or of mass. It'll be uniformly distributed mass, so it'll have a uniform concentration, and we'll assume that it's a uniform concentration at the start of the test, and then it'll be swept downstream, and we'll be interested in determining the concentration as a function of time. So let's see, we've got some global definitions here, some parameters. The parameters that we're going to be interested in, porosity, the diffusion constant, and these two dispersivities are given here. These two parameters we won't use for this exercise. The definitions, we've got these variables. Actually, this variable we won't use. This one is set up as a global parameter, but with this hydraulic conductivity, K, we will use, and that'll be applied to the whole domain. So it's just a uniform conductivity of 10 to the minus 13 meters squared. And let's see, we'll set this up with two physics. We'll use Darcy's law to determine the flow, and the properties that will be important here. The porosity, this will be a variable that we'll be changing to try to estimate. The permeability, though, we'll assume that we know that, and so we'll assign that the variable K that we decide, or we set up in the up here in the variables. And then the things that we need to know are the boundary conditions. So we're going to put a pressure head on this side of 0.1, and then a pressure head on this side of 0. So that'll give us just a uniform flow, fairly simple flow problem. Then for transport, we use transport of diluted species, and we want to do convection, and this is a porous media problem, so we'll use dispersion in porous media. The initial values, we'll set this up to be 0 out here in the domain, but the circle will have another initial value here, and it's set up to have a concentration of 1. And then we put the porous media properties in, and I did that by selecting it right there. And the porous media transport properties and it's a uniform property here. And so here's the dispersion constant, and the two longitudinal dispersivity and the transverse dispersivity are here. And so these are all the parameters that we can vary in the parameter estimation. So it's important to get these variables set up like this. And then the boundary conditions, well, for an earlier version of this problem, I had a concentration boundary over here, but we're not using that now, so we can just ignore that. But we need to have an outflow boundary here, so on the right side is outflow boundary. And what happens when we run this is we get something that looks like this. Let's kind of enlarge that. And so the concentration will start out there, and it'll move from left to right. And you can see how dispersion causes that to dissipate. Okay, so that's the forward model, and we'll want to set that up and get that running first.